for the invitation and for the opportunity to talk a little bit about my work. I was back in Montevideo in the first meeting that Sergio organized. Actually, the whole story about this South America initiative started, I guess, in a few lunches and meetings we had before or dinners we had before in Foz do Iguaçu during. Okay, nothing about the wine. Yeah. But anyway, here we are, and I think things are working, and slowly but surely. So I'll be talking a little bit about hybrid potentials and give a little overview of the work we do in the University of São Paulo, which many of you might know, but for those of you who don't know, this is the nice campus that we have in the city of São Paulo. That's the Chemistry Institute where I am based. We have right here a space shuttle just parked in front of our institute, just in case. And I run a lab there, a small lab. I've been there for 6 years, and we basically do have 3 different lines of research. We do development applications and models of we develop approximate models and potentials for molecular simulation. For applications, we are mostly interested in metalloenzymes currently, but we have done research in trying to understand the mechanism of enzyme reactions, and we are also interested in the flexibility and the molecular recognition by proteins. I'll be talking mostly about some development and the mechanism of metalloenzyme action today. So this is an outline. I'll start about hybrid potentials, hybrid QCMM potentials of quantum chemistry and molecular mechanics that are used to study electronic phenomena in condensate phase. I'll talk about the pDynamo library, which is a library, not actually one piece of software, but a library that you can build your own programs to do molecular simulation, in particular using hybrid potentials. Then I'll talk a little bit about the long-term goal of the laboratory, which is what I call computational molecular bioenergetics. We're actually trying to understand the detailed mechanism of many metalloproteins involved in cellular respiration and in photosynthesis. Then I will talk a little bit about one of the proteins, a simple iron sulfur protein that we have been working recently, which is rubidoxine. We were trying to understand some atomic force microscopy results of unfolding and iron sulfur dissociation of this protein. And we are using many different methods for that. I'll be talking a little bit about some of them. As you probably already noticed, this talk will be much more basic science than the previous one. So please, if you have doubts, if you would like to know more details about the methods or the theory behind of it, raise your hands and make questions, all right? So when you do a simulation, what do you need? What do you need to run a molecular simulation? You basically need 2 things. You need to know the composition and the initial 3-dimensional structure of your system. So be it a protein embedded in a membrane, you need to know, initial configuration for that with the solvent and all the constituents, all the composition of that system. After you know that, you need to describe the interactions, the interaction between each of the particles composing your system. Quantum mechanics, as we know, describes these interactions perfectly, but it's very expensive from the computational point of view. So it takes a lot of time to compute interactions between all the particles in a large system like this using quantum mechanics. So most of us have been using approximations to deal with these interactions. We've been talking about this, or people have been talking about this in the previous talks, like coarse grain models or molecular mechanics models. But those models are not able to describe chemical bonds. They are not able to describe electronic phenomena like spectroscopy. So what do you need? You need to use both quantum mechanics and an approximation to treat chemical reactions in such large systems. And that's the idea behind those hybrid QCMM potentials. It's actually a partitioning, an energetic and a structural partitioning of your system. So for instance, if you have your simulation box with water and your protein, and you have your active site, you will treat only your active site with quantum mechanics. All the rest, the remainder of the system will be treated with molecular mechanics, with the more approximate level. And you also need to describe the interaction between the two regions of your system. So you write down an effective Hamiltonian, which is a combination of your quantum chemical Hamiltonian, which will describe the reactive part, you know, the active site usually. You have your molecular mechanical potential that will describe the rest of the system. And you have a third part here, which is actually the different or the additional part in this hybrid potential, which will describe actually the interaction between the two regions. So what is in this hybrid interaction part? It's quite easy. You have an electrostatic interaction between the charges in your molecular mechanical region and electrons and nuclei in the quantum chemical region. And you also have a van der Waals interaction between the nuclei in the classical and in the quantum region. Okay? So your charges in the molecular mechanical region will polarize, will influence the electronic structure in the quantum chemical region. You will also have the electrostatic and van der Waals electrostatic between nuclei in the quantum, in the classical region, and you also have a van der Waals interaction between those two, the nuclei in those two regions, and that's usually described by a simple Lennard-Jones potential as used in molecular mechanical force fields. When you have, sometimes you need to break a bond between those two regions. You have one carbon, for instance, that might be in the molecular mechanical region that's bound to a carbon that's in a quantum chemical region. So you need to saturate the valence of this bond that's actually broken when you do the partitioning between classical and quantum regions. So you need sometimes how to treat with this frontier. You sometimes use a phantom or a link atom. So a little bit more detail here. When you have your hybrid interactions, you maintain many of the bonded interactions that you have in your force field, in your molecular mechanical description. So for instance, let's consider this is a quantum region of your system, and the rest of it is the molecular mechanical region. So you have, for instance, a phenylalanine here, and the ring is in the quantum region, but the rest of the amino acid and the backbone of the protein is in the molecular mechanical region. So as I mentioned, you have a bond that's broken in between those two regions. So I'll talk a little bit about how you saturate that broken bond later on, but you keep in your potential, you keep the harmonic bond term for that bond that's broken. You keep the angle, you keep the torsion, the dihedral, okay? That's necessary so that your quantum region is not fluctuating, you know, it's still part of the whole protein, of the whole system you are simulating. You also have the interactions between the quantum nuclei and the van der Waals interactions between the quantum nuclei and the classical nuclei. That's usually described by normal Lennard-Jones potential. You do have interactions of the partial charges here in the classical regions with the electrons as I mentioned, in the quantum region. And you do have to introduce a link atom. Usually you just put a hydrogen in between the bond that's broken between the quantum and the molecular mechanical region. And that's enough to saturate the quantum system, and usually it works fine. I mean, it doesn't perturb the electronic distribution in the quantum region, and you can do your calculations in the quantum part this way. So this is a typical algorithm for those hybrid potential simulations. You define those two regions. You define which atoms are in the quantum region, which atoms are in the molecular mechanical region. And then for the molecular mechanical region, you can calculate all the harmonic bonds, harmonic angle, torsional dihedral angles, contribution, the Lennard-Jones contributions, the Coulomb contributions, and evaluate forces. That's the same thing you do in a normal molecular mechanics force field calculation. For the atoms involved in the boundary, you know, in between the quantum and the molecular mechanical region, you do calculate the same covalent terms that I mentioned before. You do calculate the Lennard-Jones interactions again between the nuclei in the quantum and in the molecular mechanical region. And then the charges of these molecular mechanical atoms will enter into the quantum calculation in the Fock matrix of the quantum calculation. So when you define your quantum atoms, you need to define as well a basis set that will be used to expand the electronic density of the quantum region. And then from that basis set, you can calculate an overlap matrix. You need an initial guess of your molecular orbital coefficients, and with that three components, the orbital, the overlap matrix, the gas orbitals, and the point charges from your molecular mechanical atoms and the quantum mechanical nuclei, you can build the Fock matrix, try to diagonalize it, and then you get energies and new molecular orbital coefficients. If they converge, your calculation is done. Otherwise, you come back and iterate in this cycle. This is called the self-consistent field calculation that's done in many quantum, or in all basic quantum chemical calculations. Once you converge that SCF, that self-consistent field calculation, you can then evaluate forces, and you combine the forces that you evaluate in those three regions, or in those three contributions, and you are basically done. You can now propagate your system and do, for instance, a molecular dynamics simulation, or do a geometry optimization, or whatever calculation that you would like to do with those forces. All right? So that's the basic algorithm you do for hybrid potential calculations. The three guys that developed this technology many years ago got the Nobel Prize in chemistry 3 years ago, actually. So that's Karplus, that's Levitt, and that's Warshau. Mainly Warshau was the one developing this, and Karplus got into this area, I would say, with this paper from 1990, and the first author of this paper is Martin Field, which is who is my main collaborator, and the guy behind the P-Dynamo library, which is, as I mentioned before, it's not a black box or a closed program. It's more like a library with many routines that can do several kinds of calculations. It can do pure quantum chemical calculations, semi-empirical calculations. It can do hybrid potential simulations. It can do pure molecular mechanical as well, using many different force fields. Can do energy calculations, geometry optimization, search transition states, and a list of different kinds of simulations. So it's more like a toolkit that you can use when you're trying to do some sort of simulation. You can call the routines in this, write down your piece of code, and do your simulation. So, for instance, this is an example of a geometry optimization, a code that you need to write. It's quite simple, but it will do you the thing that the whole geometry optimization. So it's written in Python, which is more or less becoming a standard for computer, scientific computing. So if any of you guys, now I'm talking to the students, would like to learn a language, to choose a language to learn, that's probably Python you should do. So this is the code. What you do, usually you import the definitions, you import all the routines and the libraries you would like to use. I'm not showing that explicitly here, but that's what you do first. And then to do a geometry optimization, the first thing you need to do is build your molecular system. So what this routine will do, it will read this X, Y, Z file and then build a system definition for that. Now we define what energy model we would like to use. We are using a semi-empirical one, the AM1 model. So that tells the program how to calculate the interactions that, as I mentioned before. You write down a summary of your system, you calculate the initial energy, and then you ask for geometry optimization using a conjugate gradient that will actually minimize the energy by optimizing the geometry. And those are parameters, like the frequency you're going to log the calculation, how many iterations it will do, what's the convergence criteria of the calculation. And when this finish, it will give you the optimized geometry, and you can again calculate and optimize that energy and all that kind of detail you would like to have from your molecule. So that's an example. Of course, when you do a simulation with a protein, the code is a little bit more involved, but again, the idea is the same. You always, using a library, you can call this library and do your calculations. As a person that has been involved with PDynamo library, been developing for PDynamo library for almost 10 years now, I would like to advise you to be aware of some unofficial workshops and courses that you guys are given here in Brazil currently that are unofficial, and they are actually giving a workshop for an interface that they wrote that actually calls PDynamo to do molecular simulations. They are not, using or developing PDynamo itself. And I am a bit uncertain of how this library works, this interface work, and the course that they are doing. So be aware of that. That's, again, another warning for the students. So carry on. Giving a little more detail what we've been doing recently. We've been using, as I said, a fruit salad of methods. That's maybe not only 2 lemons, more a little bit lemons and apples. But as I mentioned, we work mostly with hybrid potentials. That's using PDynamo, but we've done a whole bunch of electronic structure calculations doing different programs. Molecular dynamics, different types of molecular dynamics, mostly with GROMACS, calculating free energies using different enhanced sampling methods, mostly with GROMACS and PluMed, the PluMed plugin. We've been doing binding calculations using the linear interaction energy approximation, trying to understand what's the whole of flexibility and how flexibility of the macromolecule will modulate the binding. And we also have done NMR calculations, calculating chemical shifts and derived parameters, and experiments as well. And again, that's with help from colleagues, of course. So I would like to give a little bit more details. We are planning to work and to understand in detail what's the mechanism of many iron sulfur proteins involved in molecular bioenergetics. So this is a scheme of the electron transfer chain in mitochondria. That's how all the ATP and all the energy currency is actually produced in our bodies and in our cells. And it's composed by 5 large protein complexes, complex 1, 2, 3, 4, and 5. And this, for instance, the complex 1 is a huge machine, and it has about 7 to 9 iron sulfur clusters like this one in a line here that will transfer electrons from the NIH binding site down to and reduce quinone, which is the mobile electron carrier in this protein. Quinone will be also reduced by complex 2 or succinate dehydrogenase. and then they will be oxidized by complex 3, which is cytochrome BC1, and that will allow what we call the Q cycle to happen. The Q is the ubiquinone. And again, well, the electrons will go on until complex 4, where they will eventually reduce oxygen to produce water. And complex 5 will use the proton gradient that's created by those 4 enzymes to synthesize ATP. And, well, you know the rest of the story here. But I've been interested in those iron sulfur clusters. The first time I saw this structure in the Voigt biochemistry book when I was a student, I was really surprised. And I said, wow, what the hell? What is, you know, nature doing with this cube-like iron 4 sulfur molecules? What's the structure of this? What's the electronic structure of this? And that's what I've been working mostly in the recent years. So before going for those to those iron sulfur proteins, we did some kind of molecular mechanics parameterization of ubiquinone. Ubiquinone is the electron carrier here. That's important, you know, to that will be reduced in complex 1 and 2 and oxidized in complex 3. So if we want to understand the mechanism there, we have to understand how quinone what's the mobility and how it partitions in a membrane. In a model membrane, we use a POPC as a model. So the first thing we do, we parameterize the force field for ubiquinone. That's the structure of ubiquinone. It can have a different length of isoprenoid tails, units, and we'll make a long tail. Usually mammals have ubiquinones with 10 isoprenoid units, so they will really partition into the membrane. So we do quantum chemical calculations. We parameterize a force field to reproduce those quantum chemical calculations. Then we can calculate free energy profiles of insertion of your ubiquinone molecule inside the lipid membrane. So we can do it with quinone with 1 tail, 2 tails, or 6 up to 10 tails, and calculate this free energy profiles. Of course, we are not able to converge those profiles when we have such a large molecule, but for the smaller ones, I think we are quite close to convergence in the calculations. So if you look at the numbers we get, those are experimental numbers that are measured in different compositions, the different membrane systems, and those are the numbers we calculate using umbrella sampling and bias exchange metadynamics. And while, for instance, for ubiquinone 2, we calculate this binding free energy of 21 kilojoule, which is more or less the same number as they measure experimentally. What I would like to call your attention is that, for instance, the minima, this is the z-axis, which is the normal to the membrane. So when you are in water, your z is high. When you are in the middle of the two membrane amilayers, you are in 0. So the minima is more or less the equilibrium position that ubiquinone we will assume were embedded in the membrane. And it doesn't matter how long is the tail, the ubiquinone tail, the minima will be around the same z, which is 1.8, 1.9 nanometer in the z axis. And that's, for instance, there's the same z that you will find for the entrance of the ubiquinone channel here in complex 1, complex 2, and complex 3. So nature evolved those enzymes in order to match the physical chemical properties of ubiquinone that's partitioned in the membranes. Okay, so going back for the metalloproteins, metalloproteins are really important proteins. Approximately 30% of all proteins have metals. They mostly have structural roles in the protein. They are needed there to maintain the whole the protein structure. But many of those atoms will be part of the active site or will play an important role in the chemistry that those proteins will be going on. And in particular, as I mentioned before, we would like to study the iron sulfur clusters. that are used in ubiquitously in many cellular redox proteins or processes. We will start with a rather simple iron sulfur protein, which is rubidoxine, that has only one iron center coordinated to 4 cysteine side chains. So that's the cartoon representation of the rubidoxine structure. It has those 4 histidine side chains complexed to iron. That's even simpler representation of this structure. So some very interesting and unique atomic force experiments were carried out with this protein. What those experimentalist guys do, they can produce a polyprotein, which is a polymer of proteins. They can do chemical linking to produce this polyprotein, or they can do it using genetic engineering. And you actually produce a polyprotein, a protein that's composed of many units, usually 5, 6 units of your protein. And then using an atomic force microscopy, you can actually find a single molecule chain of those proteins. And that's a representation of the atomic force microscopy tip, the cartridge that will fish the end of this polymer, and the other end of it will usually absorb it in a surface. And with the microscope, you can pull the protein. You can do it with many times. You can pull and unfold the protein. You can release the pulling, release the force, and the protein will refold. Okay, and you can measure it many times, and that's the kind of data you get. You get a profile of extension. Please notice that you have nanometer resolution here, and you can measure the force against this extension. So you measure the distance that you are actually extending your tip, and you can also measure the force that's necessary to extend that. And then you have this seesaw kind of profile. And what's going on here, actually, at each of those peaks, it corresponds to unfolding of one protein unit here. So you increase the force, the protein tensions, and eventually it will unfold, and then it will release the tension here, and the extension will increase. Okay, so it's like a spring that you put and you pull. So for instance, if you do a hybrid or a mixed polyprotein with 2 different proteins here, you will have a signature of 2 different extension lengths that will correspond to the length of each of those proteins that you gain when you unfold the whole protein. So if you measure the distance between those 2 peaks, or consecutive peaks in this seesaw profile, you end up having, you can have a distribution of folding events. You measure this hundreds of times or thousands of times, and you end up having a distribution of those events of unfolding. And for instance, if you have a hybrid polyprotein that's containing rubidoxine and GB1. GB1 is another simple protein that has been used many times in those AFM experiments, and it works like a fingerprint for your seesaw profile. And you see that more or less you get a peak that corresponds to about 13 nanometers, and another one to 18. And that's if you multiply the number of residues that rubidoxine has, that's about 55 for 0.38 nanometers, which is the length of one amino acid, you end up having this number for rubidoxine. So you know how many residues you are unfolding when you are pulling your protein. So, and of course, you can also measure the force. The force is the peak that the height of this peak that you see in the seesaw profile. And well, to unfold rubidoxine, to fully unfold that, you have to break at least 2 of those iron sulfur proteins. That's the only way you can extend the whole protein. So. Actually, what you're measuring here, the force you're measuring here, is the force necessary to break one of those, or to break two of those iron sulfur proteins. And what those experimentalists found is that the force necessary to break the iron sulfur bond is rather low. That's the force necessary to break 200 piconewtons. That's what they found, and that's the force necessary to break a disulfide bridge, for instance, which is considered as a weak bond. For instance, a carbon-carbon bond is much stiffer, is much stronger, and you need more or less 1 nanonewton to break one of those bonds. So we would like to simulate this experiment to understanding in molecular detail what's going on there. So the first thing we do is we build a model that's a molecular mechanical model, but you probably remember that you cannot break a bond using a molecular mechanical potential. So we substitute the harmonic potential, usually found in molecular mechanical force fields, for a Morse potential. That's only for the iron sulfur bond. Okay, this is a close view of the iron center in rubidoxine. And then with a Morse potential, you can actually break this bond. You can dissociate. It's only approximate, but it will describe the bond scission. So we do a steered molecular dynamics using this force field, change it with the Morse potential. And if you start from the crystallographic structure and you pull the protein, you see that your root mean square deviation will increase with time. That means that the protein is unfolding. And eventually, more or less at this region of this graph, you will have the whole protein unfolded, but still the iron sulfur cluster intact with the 4 iron sulfur bonds still formed. This rise here is when you actually break one of those bonds. And we can do the simulation for a polyprotein, like in the experiment, and we recover the same seesaw profile as the guys measure experimentally. This is the force against the extension as they do in the experiment, and this is a simulation. And those dots here are the events of when those iron sulfur bonds break. So you see you need to break at least 2 to have a complete extension of the protein. All right, so we've done this simulations. I mean, again, we can reproduce the profile, and if we pull it in different, we can pull with different velocities, you know, as in the experiment, they can control the velocity that you pull your tip in the microscope. We can do it in the computer as well. And, but the thing is that with the computer, we have to be much faster than they have to be in the experiment. That's because if you're too slow in your computer, you won't see any unfolding in a reasonable simulation time. So you pull it fast. But then we want to pull it fast, but not too fast that your system is driven very far from equilibrium. So we want to be in between. And what those 2 graphs are showing is that if you pull with 2 different velocities, like 10 to the minus 4 nanometer by picosecond, or 10 to the minus 3, you end up, or 5, you end up having the same distributions of extension and force. So we are more or less, you know, confident that we are not too far from equilibrium, or we are in a quasi-equilibrium situation. What's interesting here is that theory developed by Humer and Szabo predicts that there is a linear dependence between the unfolding force and the log of the velocity of the rate you're pulling your polymer. And well, that's the experiment, and that's our simulations. And you see that those 2 lines are more or less will be more or less coincident, or they are actually parallel. But again, there is a gap here because experiments cannot go too fast, and we cannot go too slow. But anyway, there seems to be some agreement here. But that's not telling us what's the chemistry that's going on when you break those bonds. So any chemistry student knows that you have actually 2 ways of breaking a chemical bond, a covalent bond. You can break your bond in a homolytic way or in a heterolytic way. What does it mean? In a heterolytic way, you break your bond, and the electron pair that's shared will stay with one of the atoms only. So you can break here iron sulfur bond, and the electron pair will stay with the sulfur atom, and that will be an ion. Or you can do a heterolytic cleavage, and one of the electrons will be with the thiol, the sulfur, and the other one will be in the iron, and that's a homolytic cleavage, and you end up having a radical here, a thiol radical. Well, the iron is oxidized, so it's in D5 state. It has iron 3, it's ferric state. And in the ground state, it's high spin. So the 5 electrons in the D shell are unpaired. Okay? So experimentalists were asking, what's the mechanism of this? Is it heterolytic or is it homolytic? And we were asking as well, what's the spin state of the products? Is it the same as the reactant? Are the electrons unpaired, or do they couple and end up in lower spin? So how do we do those simulations? When we do hybrid potential simulations, we always start with something we call a calibration of the model. We go back to some sort of a high-quality quantum chemical method, and here it's CEPID with a large basis set, and we do a calculation on a model system. This is, just a model of the rubidoxine active site. It's iron coordinated to methyl thiol groups for 4 of them in a tetrahedral geometry, like in the active site, and then you do the reaction of cleavage of one of those bonds. And in black, you have the sextet state, as I mentioned, with the 5 unpaired electrons. And in red, you have the energies of the quartet state, which is with only 3 unpaired electrons. You do have a pair of electrons that they coupled. So you have the energy here with a reaction coordinate. That's a reaction profile calculation. And what you find out is, again, as I mentioned, the ground state of the reactant is in a high spin state, in a sextet state. But the product, the lower energy product, is actually in the quartet state. So you do have a spin crossing in between here. When the reaction happens, you jump from a sextet to a quartet state. And we find the minimum energy crossing point here. And the second thing we find here is that although you have mostly an iron-free, formally an iron-free in the reactant, you find that in your product you have an iron-2 with a thiol radical. So the mechanism of this bond breaking is homolytic. This is, again, in our model in a gas phase calculation using a high-level quantum chemical method. But then we calculate the same reaction profile using a more approximate quantum chemical method, for instance, DFT. We tried many different combinations of DFT functionals, and we find one that works fine. And we use this combination, again, this DFT functional, in a hybrid potential calculation. And now I'm back to the whole protein. So I get the rubidoxine unfolded structure, but just a little bit before of the iron sulfur bond breaks in that simulation I showed you before. And then we calculate again the reaction profile for the iron sulfur bond cleavage. So that's the product, the geometry of the product with the bond between cysteine 5 and iron broken. And again, you see the same sort of profile you see in the gas phase with a crossing point between the sextet state and the quartet state. And you do have, again, a homolytic cleavage in the reaction mechanism. Experimentally, they measure, they estimate a barrier for this reaction of about 8 kilojoule per mole, and in our calculation we find about 100, so it's a decent agreement with experiment. In experiment, if they release the force, they will see spontaneously the protein refolding. Well, that's in agreement with the very small barrier that we have here, so that will allow the refolding, the reverse reaction of iron sulfur bond formation. And well, we find different other details about that compare with experiment as well. There is one thing, interesting thing, and I'm getting to the end of this talk, but there is one interesting thing about those metalloproteins, experimentally, it's very hard to study their reactivity because those metal centers are very reactive, and evolution has evolved, nature has evolved proteins to enclose the metal center, usually inside those proteins, to protect them from other possible reactants. So it's very hard to study their reactivity in situ, in the protein. You can unfold your protein, rise the temperature, but then you will uncontrol the unfolding, and it will be a little bit difficult to study what's the whole of the protein environment in the stability of the chemical bonds with the metal. So using these techniques, this atom force microscopy, as you have seen, you can control the unfolding of the protein. You can unfold it partially and expose your active site partially as well, in a controlled fashion, and that will allow reactants that are dissolved in the solution to access the metal side and do chemistry. So we can, and in collaboration with the experimental people, we have studied what's the reaction of, for instance, a nucleophile will compete for the iron center, and what reactions it can do with the iron center in rubredoxine. Well, to break two of those iron sulfur bonds, you can first react with one of those thiocyanate molecules, and then you can react with a second one, and you end up with this sort of product that will have two iron sulfur bonds broken. Or you can even react then with water and then with thiocyanate, or first with thiocyanate and then water, and again you end up with two of those bonds broken. So we calculate the energy profiles again for those reactions, and we see that we find the lower barriers, that's probably the mechanism that nature will go on, with the first, the water reaction, which is this reaction, and second, the thiocyanate reaction. So that's got a barrier of about 70 kilojoule per mole, which is smaller than the barrier found in the absence of those chemical agents. Again, if you go, I'm not showing the experimental data, but that's exactly what you find when you do the experiment. You see that the bond in the presence of thiocyanate will break in a lower force, so it means it was destabilized by the presence of those reactants. We can do the same thing with acidic media, changing the pH of the system, and for the pH you can protonate your leaving group, and then you have much lower barriers, much lower barriers, and faster reaction and lower forces to break the bonds, and we can actually calculate the force that's necessary to break the bond in this rate determining step. And that is again in reasonable agreement with experiment, showing that the force to break the bond will decrease when you include lower the pH, or when you include the thiocyanate. So with that, I would like to thank Martin Field, which is my collaborator in many of those iron sulfur studies I mentioned. Hongbin Lee, who is the experimentalist that runs this AFM calculations. Hongbin is coming to Brazil in June to participate in the SBBQ, in the Biochemistry Society meeting, and he's giving a postgraduate or a graduate course in AFM of biomolecules in our institute. So all of you who are interested in that, please get in touch, and you are more than welcome to participate. I also would like to thank my research group. Ariane has done some of the simulations with the MOS potential for unfolding of rubredoxine. Murilo and Rafael, who are here, have done different work which have not shown, and Vanessa has done the calculations of ubiquinone parametrization and insertion in the membrane. Vanessa now has left the lab. She finished her postdoc with us, and she got a position in Mendoza in Argentina. I would like to thank FAPESP for all the money that we have to buy computers and to do research. And say that we are open. We are always happy to receive master's and PhD students as well as postdocs. And before I leave you, I will leave you some of the references. Those are the experimental unfolding papers of using an AFM. That's the Vanessa paper with the ubiquitin parametrization and simulations. And those 3 papers will describe the iron sulfur reaction studies that I'm showing you. So thanks a lot for the attention.
Questions?
Okay, nice work. You have shown that when you add a nucleophile, the force you require to break the bond is lowest. The experiments are performed in vacuum or in water?
No, in solution, yeah.
In solution. And then how do you, and your simulations were performed also in solution?
Yeah, yeah.
Ah, okay.
But yeah.
Okay, the representation of the bond was simple, but do you see the substitution of the iron sulfur bond by water?
Yeah, it's those reactions. That's what I'm simulating.
No, but I'm saying that in the classical simulation.
No, not in the class. So that's a hybrid potential simulation, yeah.
But in the classical simulation, that was performed in solvation
as well. No, that was done in implicit solvation. Yeah, but that's just a mechanical model. So we are not looking at the detailed mechanism of bond breaking. But the agreement
of the forces was reasonable. So
but that's a calculation done in a hybrid potential. We measure the force just a derivative of the energy curve. So the classical simulation is done only to prepare the system. We use our geometry just before the bond is broken to do the hybrid potential simulation. And then we solvate the whole system, and then we equilibrate that with, we fix the pulling distance so that, the protein doesn't refold. And, well, there's care with the model, I guess. Yeah.
Okay, so is it possible to couple experiments with when you are doing the experimental cooling?
Yeah, they are doing it.
If you are changing, I guess if you are changing the returning state of iron, you should see some change in its spectrum.
Well, that's what the experimental people are working on, the coupling, the instrumentation to be able to measure visible or EPR spectra, for instance. Yeah. That's ongoing work, but that, it's much easier to do in a computer.